All right. So our plan today is to finish up the rest of chapter 16, and there's not a whole lot to it. You would have been doing a multi-week lab on qualitative analysis if we were still in class, if we were still in the laboratories, but unfortunately we're not going to be able to do that. But I'm going to kind of walk through the idea of qualitative analysis with you. Unfortunately, since you don't get the experience, you're not going to get the total package of this. But it's a fairly simple concept that utilizes the solubilities of different substances, and it does so in a way that allows you to identify what types of metal ions and oftentimes what types of cations are in a given solution. Which is important for things like water analysis, right? If you're monitoring the types of ions that are in water, you can make sure you have nice clean water, which is obviously a problem in certain places like Flint, Michigan, and I think it was Newark, New Jersey is another one that has had lead in the water in the past. And so this type of analysis, like I said, it relies on solubility chemistry. But the whole idea is that you're using the solubility of various substances to identify the presence of certain ions. And so, like I said, we're going to just really just kind of scratch the surface of this. Ideally, you would actually get to do it in practice, because in practice, I think is just a much better experience and really helps to learn this type of analysis. So here's the basics of it. If you have a solution, and that solution can have all kinds of different potential ions in it, right? So are the ions that we could say are possibly present in a solution. Here, we're just going to look at cations. There's a totally different procedure for anions that we're not going to focus on, but there's some basics of this, okay? So if you were to take a solution, and you don't know what's in it, except you know that it has some cations in it, you could start to add reagents to it, and based on the reagents that you add, you could cause certain things to precipitate out. For example, if you add HCl, right, if you add hydrochloric acid to a solution, one, you keep the solution so that it's acidic, because a number of anions that could also be present in the solution are conjugate bases of acids. So you want to keep the solution acidic initially and really see what precipitates out with, in particular, it's this chloride. Right? So you can precipitate things as chlorides, which is something you've done in the past in Chem 101 when you did gravimetric analysis of a chloride salt. Oh, this I'm noticing is not correct. This should be just AgCl, not AgCl2. And so if you add chloride, that chloride will cause certain things to precipitate. So silver chloride, right? Mercurous chloride, lead 2 chloride. Those are all things that would be insoluble as a chloride salt. And so what you do is basically you say, okay, if I can get those to precipitate out, and then maybe I can go and do some other analysis to get those, to identify the 3 different substances, to identify and distinguish between the silver or the mercurous ion or the lead 2 ion. But that's how you would do it. You would basically just say, I can get these 3 things out of solution as chloride salts. Everything else is left in solution, all of the other cations. Once I have it narrowed down to these 3, I can do other procedures to identify which of those 3. And that's what we're losing really out of this, is seeing what different things you can do to identify not just the things that are chlorides, but the chlorides distinguished from the chlorides as well. But what you would have left after that is all the ions that remain soluble, that did not precipitate out as a chloride salt. And so once you have that, you've got a solution of chloride. Well, of the ions and chloride, and maybe other anions as well. And so then you can add the next thing, which is this hydrosulfuric acid, H2S. And so that keeps the solution acidic, but the sulfide reacts with other things to form sulfide salts, which are insoluble. And so those would precipitate out of solution as sulfide salts. So you'd have bismuth or cadmium or copper or the mercury 2+ ion or tin 4. Those are all things that, again, you could go and do other steps on to identify which ones you have, if you have one or more. But that then removes all of the bismuth and the cadmium and the copper and the mercury 2 and the tin 4. And so you know that there's none of that left. So after steps 1 and 2, whatever's remaining, now in that solution that's remaining, you have a bunch of sulfide and some chloride and some hydrogen ions. So it's a very acidic solution right here, right? It's very acidic. And so the next thing you could do is say, well, okay, in that first step of adding the hydrosulfuric acid, when you add that, you're actually precipitating things out that are very insoluble with sulfides. And so the next step would be just adding some base to neutralize and make the solution basic. So you add some sodium hydroxide. When you do that, you actually precipitate out a couple things. One, you precipitate out the sulfides that are less soluble, that are more soluble than the sulfides in the first step, right? Remember, the sulfides you precipitate out here are very insoluble with sulfide. The ones here are a little bit less so, because those ones allow the sulfur to remain as hydrogen sulfide in a given solution. And so they don't, basically the equilibrium between the metal and the sulfide is affected by the acidity of the solution. And that's something we talked a little bit about last time for sort of the acidity and how acidity affects the equilibria. But you'd also be precipitating out things that would go as hydroxides. So if you take out something like the aluminum and chromium hydroxide, you could potentially separate that out doing subsequent analysis as well, because those are also insoluble substances, and you could do other analysis to figure out which of those ions you have. But now you've gone from an acidic to a basic solution. And so the next step is to switch, because the ions that we have so far, things like sodium and chloride and protons, well, the protons we've mostly removed by adding a lot of base. You might have some sulfide in there left over as well. And going into the next step, you can add something like sodium carbonate. So adding sodium carbonate, well, that gives you a solution. It's a basic solution. So the carbonate isn't really going to be particularly well protonated. So it's this weak base. And so you're going to have that reaction of the weak base with things that are insoluble as carbonate salts. So barium and calcium and magnesium would be examples. And again, you can do subsequent analysis to see which of those is which. Okay. The last thing you'd be left with is salts that contain the ions like potassium, sodium, ammonium, maybe lithium. And so those are all the alkali metals. And those alkali metals, again, you could have other analysis. With alkali metals, a lot of times what you do is a flame test in many cases, which basically you take a little bit of the sample and you put it into a little bit of fire and it burns a certain color depending upon the excitation and emission spectra of that substance. So something like sodium would burn with this sort of a yellowish, orangish yellowish color, whereas something like ammonium is not going to really give you any color at all. So that's the idea of how you might do something like this. And it's really important if you're looking at sort of the purity of a solution, you're testing a water sample of something, that's an important thing for you to know. Now, it's all qualitative. So you're just looking for the presence of something. You're really not looking for the concentration of it that you might in a more quantitative technique. Unfortunately, that's all we're going to get to do with this because that particular lab is, it's out since we're not in lab to do it. But that would be the process of doing this, and you could identify what's what based on this flow chart. And so the flow charts like this are actually used in quite a bit of chemistry. And if you go on to organic chemistry, you'll likely be in a lab by then, at least I hope, and you'll be able to do some more chemistry that involves sort of tracking what's in what solution based on the chemical properties of the things that you've added and the reactions that have taken place. But that's the idea of qualitative analysis. You're using things like solubilities of these substances to distinguish what is in a solution so that you can identify the impurities of that, for example, water solution. Okay. So the next thing to talk about, and we're just going to scratch the surface on this one here, is equilibria involving complex ions. We're going to touch more on this sort of way towards the end of the term when we start looking at transition metal chemistry. Okay. But a complex ion is something that is found in a lot of places, and so you really need to know what it is before we go too far. And so we'll talk a little bit about what it is, and then the nature of the equilibria involving these complex ions. So first and foremost, our complex ion, okay, is it's really, so it's an ion similar to in a way similar to your polyatomic ions in that there's a lot of atoms that compose this ion. It's also largely covalently bound, but in a different type of way. But this one also includes these metal ions. So it's a complex ion. It's basically got a metal ion of some kind, aluminum 3+, silver plus, copper 2+, copper 1+, depending upon the oxidation state of the metal and the ligands, you can get lots of different possibilities for a substance. Now that leads to the next thing, which is the ligand. What is a ligand? So we've only briefly talked about what a Lewis base is so far. The idea of a Lewis base is it's an electron pair donor. And so when it donates that electron pair, essentially what happens is it forms a bond. So we've looked at Lewis base from the standpoint of acid-base chemistry only, but we really didn't get into it because this is sort of a more important time to really think about it. But when we think about a Lewis base, right, something like water acting as a Lewis base, right? Water has a couple of lone pairs of electrons, we know, and water acts as a Lewis base with the hydrogen ion, right? And so in that case, you have this lone pair of electrons that comes over here and is donated to form a bond. So what does that mean? Well, first off, we make the hydronium ion from this particular reaction, okay? Now what's happening is, based on our requirements for a bond, right? A bond, remember from a bond, in order for it to have a bond, we need two things. We need overlap of orbitals from the bonded atoms. So in the case of water, so you're looking at that water molecule. So it's the lone pair sits in one of those sp3 hybridized orbitals. And the hydrogen ion has that empty, in the case of the hydrogen ion, an empty 1s orbital. So when the bond forms, you have this empty 1s orbital that overlaps with an sp3 orbital. In the case of a ligand is forming what's called a coordinate covalent bond, okay? So a coordinate covalent bond is a type of covalent bond where you still have the two orbitals that overlap, but the electrons are both donated by one element in the bond. Okay, so in that coordinate covalent bond, and that's sort of the take home here, it's still a covalent bond, you still have overlap of orbitals, but the key take home of the coordinate covalent bond and how it differs from sort of more traditional covalent bond is that both of the shared electrons come from the same element. Okay, and that element is part of that Lewis base. Okay, so that's sort of just an introduction. We'll draw this out a little bit more in a minute. We'll see what's happening in some solutions. But that's sort of the overall gist of transition metal chemistry and coordinate covalent bonds and complex ions, how complex ions can form. And so the coordination number is sort of the last of these things to bring up. So when we talk about a coordination number, what we're talking about here is really just the number of ligand atoms bonded to a central atom, okay? So the reason I specify ligand atoms here, I'm losing my pen's not working. Try this, there we go. Hold on, I'm having a little trouble here with my PowerPoint slides. What is going on? It does not want to go. Ah. One moment. There we go. Okay. Sheesh. All right. So, with the coordination number, right? It's the number of ligand atoms bonded to the metal ion, and I specify in this case, in particular, the number of ligand atoms, not the number of ligands, because as we're going to find out later on when we get into chapter 21, which is the last chapter we're going to look at, there are ligands that will bind to a metal in two locations, or two different atoms will bind to a ligand, or maybe 3 or 4 or 5 or 6. And that is something we're going to get into a little bit later. But if we just know that each atom that's bonded to the metal ion is going to be part of that coordination number, right? So the coordination number is how many ions are, or how many atoms are attached to that ion. Now this is different from the steric number to some degree, okay? The steric number is how many different electron groups there are. So the steric number includes the total number of lone pairs of electrons, whereas the coordination number is talking about just the bonded atoms. Now, something else that's important that we'll sort of talk about and get into in a second, this idea down here that metal ions can be assumed to add ligands one at a time in steps characterized by equilibrium constants. And these equilibrium constants are just, it's an equilibrium where we add these ligands, and those are described by a Kf. It's just the formation of this metal ion, okay? Now, we're gonna look at this and how this works for a couple, or for in really one particular situation first, okay? And that situation is silver forming the silver compound that has 2 ammonia molecules attached to it, okay? Now, the way that this is gonna work, if I think about what a silver ion is, right? I've got this silver plus. Now that silver plus is an ion. It's got some orbitals that are available. And that silver plus will have 2 ammonia molecules. And so I'm going to try to draw this out a little bit in terms of the perspective drawing. Make it a little bit better. There we go. Right, but there's also this lone pair of electrons on an ammonia molecule. And that lone pair of electrons can be what forms overlap with a bond or an orbital from the silver ion, right? So essentially you could say that the silver ion, right? If you've got the silver ion here, it has an orbital here, and the ammonia has an orbital, right? We know for the ammonia that it's an sp3 orbital because we've done our Chem 101 work. And this lone pair of electrons is coming from that ammonia molecule and forming the bond there. And then you would have a second one that would also bond to that. Now, the number of ligands that would attach to a metal is something that really has to be experimentally determined. And we're not going to get into that kind of reaction. That's really that kind of an analysis. That's an analysis for something that's really an upper level course, okay? But with silver will have 2 ammonia molecules that will attach to it. Now, when we say they add stepwise, you can think about this as being equation 1, where the silver ion reacts with the ammonia ion to form this complex ion. This is a complex ion here. Okay, and that complex ion has an equilibrium constant associated with it. So you could say, oh, well, that has an equilibrium constant. That is going to be the concentration of the silver in H3 plus complex ion. We'll also call these complex ion just a complex. So if I don't say ion, it's the same thing, right? That divided by the silver ion concentration times the ammonia concentration. So one of the things to keep in mind here is that these equilibrium constants, you'll notice, that's 10 to the third, right? So these tend to be pretty big, which means that the forward reaction is very much favored. So you're really making all of this stuff that you can. You're taking and making a lot of product, basically. It's very product favored. If you were looking at K2, right? So you could add a second ammonia in there. And so in that second equilibrium, you're really looking at, as an equilibrium constant expression, this silver with 2 ammonias attached to it, with a +1 charge, okay, divided by the concentration of the silver with 1 ammonia times the ammonia concentration. So oftentimes, so what you do is the first equivalent, if you will, of ammonia. So if you start with 1 mole of silver and you add 1 mole of ammonia, you make all of that first substance here, right? If you add a second equivalent after that, you would then start to form more of this. And again, this has a very large equilibrium constant as well. So both of these equilibria are large, and they're going to push the reaction toward the products. Okay. So when we think about these formation constants, it's also, we're going to make essentially this this overall product here by adding in a bunch of ammonia. Now that ammonia that we add oftentimes is going to be a very high concentration. You actually did a bit of this with your equilibrium constant experiment, where you added in a bunch of the thiocyanate, I believe is what it was, that you had with the iron, right? So you had a very high concentration of the ligand. So you've already done some metal ligand chemistry in lab. Now, the complex ion is going to be fully formed in a lot of these reactions where you add just a bunch of ligand to make sure you push that reaction, right? If we add a lot of the reactant, we push the reaction even farther to the right. And so a lot of these experiments and the formation constants that we look at will be used for looking at things like solubility of a metal in a solution that may contain some of these complex ions. Now, in order to figure out and see what's happening in this chemical reaction, something I want us to take into account is the idea that this is a silver, ion that is aqueous, okay? Now, because the ammonia, right, ammonia is a Lewis base, right? It's got a lone pair of electrons to donate. But when I think about what silver is and how I get that silver ion into solution, well, I would get that silver ion into solution by dissolving it as something like silver nitrate, right? Well, silver nitrate, we know, is soluble, and so it's going to dissociate into silver ion and nitrate ion. And that KSP is very large, right? We know it's very large because nitrate salts tend to be very, very soluble. So it's pretty much, as we've said in the past, it's going to dissociate completely. So what's really going on there? Well, when you have the silver ion, what you're actually making is a complex ion of the silver dissolved in water, because the water is acting as a Lewis base as well. And so a lone pair of electrons from water will actually overlap, the electrons in an sp3 hybridized orbital from water, that sp3 hybridized orbital will overlap with an orbital from the silver. Don't worry which one yet. We'll deal with that when we get to chapter 21 stuff. But it'll form a coordinate covalent bond with the silver ion. And so what's really happening is, in a solution where you have silver ion that's aqueous, you have something more like this, and there's some subtle differences to that as well that we'll look at later. But the thing that's really going on with these formation constants isn't just that your silver ion is reacting with the ammonia. What's actually going on is you have this silver ion with water attached to it, and the first equivalent of ammonia goes in and kicks out one of those water molecules, right, to form a complex ion that looks like this, which is what we call shorthand. We call it the silver that's attached to the ammonia rather. Well, then you can take that one and add another equivalent of ammonia and wind up with this silver complex with two ammonia molecules attached to it as ligands. Okay. Now, why is it that the silver would prefer to bond to the ammonia over the water? Because you think about it, the water is a very high concentration, right? If you just have a liquid water, it's a 55 molar solution. So the concentration of water in an aqueous solution is pretty close to 55 molar. Whereas the ammonia, maybe you put in 1 molar worth of ammonia. There's a competition there for which type of molecule bonds to that silver ion. And that competition has to do with how good of a Lewis base is that ligand. So which is a better Lewis base, water or ammonia? And you can tell that for the most part based on how good is it as a Bronsted-Lowry base. Ammonia is a much better Bronsted-Lowry base than water is, right? Water's Kw, which is the equilibrium constant for water acting as an acid and a base, right? That's 10 to the minus 14. For ammonia, right, it's a much larger value, more on the order of I think it was 10 to the minus 5 for a Kb. So ammonia is a better base, right? Ammonia overall, right, and that's the key here, is a much better base than water is. And so a better base usually bonds more strongly. And I went through all of this stuff. You don't necessarily need to know all of this stuff yet, but this is sort of that prequel to the chapter 21 stuff. It would have been nice to have the chapter 21 stuff before we got here, but since we didn't, I figured we'd go through a little bit of the foundational chemistry that's involved with the bonding of these ligands to the complex ion. It's just to give us a better feel for what's going on in that solution. Okay. So with that in mind, understanding concentrations of ligands compared to the concentration of the metal ion is important. Okay, so those tend to be much higher in concentration. I mentioned this before. They tend to be very much higher in concentration than the concentration of the metal ion. Okay, and so that competition that we're talking about for which is the better base, well, you know, ammonia is a better base than water because that ammonia is going to rip away the proton from water to form the ammonium ion and hydroxide. But also something to know is, in a solution, you also have something like hydroxide, and hydroxide is sort of also in competition. So there's a lot going on in the solution. And so you have a lot of potential ligands in a given solution that could potentially bind to a given metal ion. Now, when it comes to the ligands, well, we have amines and hydroxide. Both of those are better bases than water. okay? And that's a key here. Both of them are better bases than water, but what winds up happening is the chemistry involved with the actual overlap of the orbitals often has something to do with sort of size of the atoms that are bonding and where they are on the periodic table that's just beyond the scope of this course. Suffice to say that when you have a ligand like ammonia will react really well with transition metals, and hydroxide doesn't do that so much. Whereas if you look at later transition metals, post-transition metals, things that are in the main group out to the right of the transition metals, those are going to tend to react well with something like a hydroxide, but they won't form these complex ions with something like ammonia quite so well. But for example, aluminum hydroxide forms a complex ion in a kind of an interesting way, where if you think about aluminum hydroxide, right, AlOH3 is insoluble for the most part. It's got a very low solubility. But if you have an excess of hydroxide, if you add another hydroxide in there, it actually will react with the aluminum hydroxide to form a complex ion. Okay, and that will be soluble. So there's a little bit of interesting things with the chemistry here, but aluminum, right? Aluminum is to the right of the transition metal, so that's going to react better with hydroxide, whereas most of the transition metals are going to react more with ammonia. That being said, there's a lot of trivia in this that I'm not forcing you to memorize. If you get a question about the solubility of a complex ion or something like that, you're going to get plenty of background information to help you sort of navigate that question. I'm not expecting you to memorize solubility, but you should know transition metals tend to react more with ammonia. Post-transition metals, things to the right of the transition metals in the main group, tend to react better with the hydroxide. So, a lot of background information there. Now, we're going to get back to sort of the original format and start to see how this particular type of equilibrium works. So we go back to our original reaction again. This occurs in steps. So if you add two equivalents of the ammonia, the first one's going to add to all of the silver ions, and the second one will add after we add that second equivalent. But you're not going to make a big mixture of these two things. That being said, also, you will have some mixture because these are in equilibrium with each other. So you will have some of each of the components in a solution that you have a mixture. So you might have some silver ion, some ammonia, the silver with one ammonia in a mixture of any amount of this. And then you might also have some silver with two ammonias bonded to it. And that's going to largely be dependent upon those equilibrium constants and the concentration of the ammonia. Right, but the ligand concentration is going to have a lot to do with how much of each of those other things are present in a given solution, right? The silver ion, the silver with one ammonia, and the silver with two ammonia, okay? But it's all just equilibrium chemistry that's all tied together. But we know that those Ks are large, so each of these reactions is going to lie toward the right, okay? And overall, if you add two equivalents, you can add those equations together. And when you add those equations together, you get an overall chemical reaction like this. And this would have a Kf associated with it equal to, well, the concentration of the complex ion two there, divided by the concentration of the silver ion times the concentration of the ammonia squared, okay? So we're going to use that information as we do a practice problem. In this practice problem, we're going to figure out, so if you have two solutions, one of 1 times 10 to the minus 3 molar silver nitrate mixed with another 100 milliliters of 2 molar ammonia. So in this case, again, you'll notice that the ammonia is much higher in concentration than the silver ion. So what are the concentrations of all the species present once equilibrium has been reached? So for this, what we're going to do here is really just, first off, write out the chemical equation that governs this. Now we have a huge excess of ammonia, so way more than 2 equivalents. So we're going to look at the equation here to begin with, okay? So we've got silver ion, and you don't need to put the nitrate in there because that nitrate is just a spectator ion for this reaction. So the silver ion reacts with the ammonia to form the silver ammonia complex. And that's also soluble. And with so many of these equilibrium problems, we're going to put together an icebox. Okay. So in this icebox, we have these initial concentrations. Remember though, we're doing a dilution, right? So we have to do a dilution. If we mix two things, I've got a solution of 100 milliliters of silver nitrate and 100 milliliters of ammonia. So I have to do, when I go to put my icebox in, I have to do that with the combined volumes. So we're looking at after they've mixed, what happens, which means that the concentration of the silver nitrate is going to be half of what it is up here, because in this case, we're doubling the volume. And so our initial concentration of the silver ion is going to be, 5 times 10 to the minus 4 molar, I guess 5.00, right? The initial concentration of the ammonia is, well, that's also going to be cut in half because of the dilution. So it'll be 1.00 molar. At the beginning of this, we're going to say, well, we don't have any of that complex ion because they haven't reacted yet. Now, another thing for us is that when this chemical reaction occurs, we're going to use up almost all, right? So I can say minus about, and I'm going to put that there sort of for a reason. I'm basically saying in this initial calculation, we're going to say, yeah, we're going to use up all of that silver ion because those equilibrium constants that we talked about up here, right? Since they're really large, we're gonna go in and look at those as being since they're large, it's going to push that reaction toward the product, which means we're going to use up all of the silver ion. So those will be times 10 to the minus 4 for the silver ion. And so at equilibrium, you'll essentially have no silver ion left. But that's something also that's not totally true. There's going to be some, it's just a small amount. And we'll calculate that in a little bit. Hardly any, but it's still there. So we're going to still be able to calculate how much is left. Well, when it comes to the amount of ammonia that gets used up, well, I use 2 ammonias for every one of the silver ions. 0.00 times 10 to the minus 4. Okay, so if I use that up, okay, so 1 minus, well, 2 times 5 times 10 to the minus 4 is going to be 1 times 10 to the minus 3. That's essentially still 1 molar. Okay, that's left over. A little bit less, but it's still pretty close. Okay, and so we can actually take that into account if we want to. We can take it into account when we do our calculation, but our calculation is close enough to 1 molar that we'll probably just do that. But for the silver complex, well, since all of the silver gets used up, we're going to make all of the silver complex. So for that, we're going to make 5 times 10 to the minus 4 molar silver ion, so that at equilibrium, okay, it'll be 5 times 10 to the minus 4 molar. And the reason we can say that again is that the equilibrium constants, one, the equilibrium constants are very large, and two, you have a lot of the ammonia in this solution. Okay, so if we do this, we now have two species that we know in this solution besides the water. We have our concentration of the silver complex, okay, which is approximately equal to 5.00 times 10 to the minus 4 molar. And we have the concentration of the ammonia. Oop, try that again. Oop, not NH4. What am I doing? Not ammonium. Come on. There we go. Concentration of the ammonia is basically that 1.00 molar. So we've already figured out the concentration of two of those four things that are in the solution, right? So we've already figured out the concentration of the ammonia and of this, at least to a certain extent. And we're going to use that in the next step to figure out the concentration of the other things. And since our K1 from before, right? Remember that's equal to the concentration of the, actually, we're going to start with, we're going to start with K2. Let me erase that, take a step back. Come on, there we go. So we're going to start with our K2 actually. What we know about K2, right, that's the concentration of the silver complex with the 2 ammonia divided by the concentration of the silver complex with 1 ammonia times the concentration of the ammonia. Okay, and so we can rearrange this equation so that we can solve for the concentration of the silver complex with 1 ammonia that remains. It's going to be small, but it's still going to be there, so we should calculate the concentration if we're looking for all of the species. And that's just a quick rearrangement of that equation. Okay, and so here we can just plug in our numbers. We can go back, or we can see that we'll take our first part is just this 5.00 times 10 to the minus 4 molar, right, of the silver complex that we had from up here. Divide that by if we go back to our equilibrium constants, we've got the 8.2 times 10 to the minus 3 for K. And then we have the concentration of the...
I think it's 8.2 times 10 to the 3.
Oh, sorry, times 10 to the 3rd. Yep, you're absolutely right. See, I always do that. It's that transition from going from weak acids to not weak acids. I'm going to go from very small to not so small. Oop, I totally can put in the number for that. It should just be 1 molar. And when you do that math, you wind up with a value of about 6.1 times 10 to the minus 8 molar. And that's, again, that's the concentration of the silver with 1 ammonia on it. okay? And we can use that information in K1, which is the silver with 1 ammonia. We'll finish up this calculation and then we'll call it for the day, and we'll finish up a little bit more on Monday. So that'll be over the silver ion concentration times the ammonia concentration. And so again, a rearrangement says that you can find the silver ion concentration. Again, this is going to be really small. And we plug those values in. So we have our 6. Again, come on, pen. There we go. Okay, so we get our 6.1 times 10 to the minus 8 divided by our K1, so 2.1 times 10 to the third. Times 1 molar. And you wind up with a value for the silver ion of 2.9 times 10 to the minus 11 molar. Okay, so there's our other two values. You can see though that the amount of silver that's remaining, right, 10 to the minus 11, that is really, really tiny. But you can basically use just these equilibrium expressions to figure out what the concentration of these ions are at once this reaction reaches equilibrium. Okay, and so we're going to end it there. I'm going to start your and then we'll start the quiz. And so let me stop our recording.